Our learning goal is to apply Kirchhoff's laws to solve circuit problems involving series circuits. So before we begin to try to solve for the unknown variables of this circuit, there's first a couple rules that we got to talk about. So this is the first law that we're going to apply. So if we look here, try to look at the pictures and figure out what the first law is about. Remember, I stands for current. Okay, so in this first picture, we've got I1, I2, I3, I4 in this equation. In the second picture over here, it shows electricity. Okay, we got 15 amps, 5 amps, 10 amps, and then it shows a water analogy. So 15 liters per second, 5 liters per second, and 10 liters per second. So from these pictures, hopefully you can figure out that the first law says the current into this section right here, when it splits off into two directions, is called a junction. But the current into a junction is equal to the current out of a junction. Looking at this one, the current into the junction, I1, is equal to the current out. If we add up I2, I3, and I4, that would be the current out of the junction. So if you're taking a note on your page, we can say law 1, current in is equal to current out. And maybe a picture might help you with this one. So I've got I is equal to 15 amps, and that splits off into, let's just say, 5 amps and 10 amps. The second law, let's see if you can look at these pictures and figure it out. Okay. So, hopefully you're able to realize that with the second law, it can be written this way. The sum of the voltages around any closed loop is 0. So, when we talked about voltage in class, we said volts, is the number of joules per coulomb that you have. So we talked about our pretzel analogy, right? So you start at the battery, and each coulomb of charge, which is each person, coulomb is the person, picks up a certain number of joules, which in our case was pretzels. So let's just say you walked through this battery and you picked up 14 joules, 14 pretzels for each coulomb of charge. And then you walked around, and if there were two identical resistors, if it was series, you would go and you drop off 7 on the first one, 7 pretzels or 7 joules per coulomb. And the second one you would also drop off 7. And then you would have no more pretzels as you walk back to the battery. So that's essentially what this second law is saying, is that if I started the battery and pick up 14 joules per coulomb, I have to lose those 14 joules along the path when I get back to the battery. So we can write that down. Law 2. Sum of the voltages in a closed loop is equal to 0. So let's just apply that second law to this first problem. It says my total voltage, so this is the voltage of the battery, is 9 volts. So meaning all those 9 joules per coulomb have to be lost in all three of these, because this is my only closed loop in this circuit. So we're not sure how much is going to be lost in each. It could be 3, 3, 3, or it could be 4, 3, 2, but we'll have to figure that out. Now, this problem, it tells us something about the resistances. 3, 3, 3. So you might remember when it's in series, the resistances add normally. So the total resistance is going to be 3 plus 3 plus 3. Well, because it's series, my total resistance is 9. The last one that we can apply is Ohm's law, which says for an ohmic material, voltage is equal to current times resistance. So we can apply that to this, our total battery here. We have 9 volts is equal to I total times 9 ohms. So my current must be 1 amp. Okay. Now from here, again, we know that these three numbers are going to add up to give me 9 because of the second law here. We don't know how much in each. The current, though, is 1 amp coming out of the battery. So remember for a second, current is measured in amps, which is the same as coulombs per second. So think of this as people. Remember, coulombs are people. So people per second. So I have 1 person per second moving through here. So he's got that one person has to go through this one, and that one person has to go through this one and through this one. So the same number of coulombs per second that pass a point coming out of the battery has to pass through this first resistor, the second one, and the third resistor. So these are all going to be 1 amp, 1 amp, 1 amp. We didn't need to apply the first law because there was only one path to take. When we look at parallel circuits, that's when our first law is really going to come in handy. So here I can use Ohm's law again. V is equal to IR. My voltage, we're not sure. Current is 1 amp, and my resistance is 3 ohms. So my voltage is going to be 3 volts for each one of these. It turns out to be the same because they all have the three have the same resistances. But if these had different resistances, these wouldn't necessarily be the same number. But we would know, based off of the second law, that these three numbers would have to add up to 9. So you can always do a check that way. Do these three numbers add up to 9? Yes. Okay, we did this correctly. So we're going to look at one more problem. This one, we have a little bit of different information. So we've got 12 volts for the battery. And again, I know that these three numbers are going to add up to 12 based off of our second law. The sum of the voltages has to be 0. Well, what other information I have? Look at this, 1 amp. That's useful. It's telling me the current through this resistor is 1 amp, but it's a series circuit. So the current that's going through R2, well, that has to be the same as the current going through R1, which has to be the same as the current going through R3 and the same as the total. This is 1 person per second passing this point. If you want to think of this as cars on a highway, well, this is 1 car passing this point. Well, that 1 car has to pass this point, and this point. So I can put 1 amp for all of these. Now I look, well, I have these two, I can find the third using Ohm's law. Same with this. I have these two, I can find this third using Ohm's law. So let's do that and see what we find out. So 4 times 1 is equal to that voltage. So this is going to be 4 volts. Over here, if I look at this one, 12 volts is equal to 1 amp times R total. So R total has to be 12. And now we've got to figure out, okay, what other information can I find? Well, if you're not sure, you think back to your two laws. How can I apply the first law and how can I apply the second one? Well, the first law has to do with current, right? The first one has to do with current. So we figured out all of our currents. So we're done with the first law. The second law has to do with voltages. Remember, the second law was saying, okay, 12 volts battery, meaning 12 joules per coulomb, or I'm picking up, when we were walking this, you're picking up 12 pretzels, and you've got to lose all 12 of those when you go through these three. Meaning, from the second law, 12 is what I start with, and I've got to lose that from V3 plus V2 plus V1. Well, I have some of these numbers. I have 12, I have V1, and I have V3. Got 5 there. I'm not sure what V2 is, but V1 is 4. Right? 1, 2, and 3. So I can figure out what that last one is, right? Subtract 12 from 5 and 4. So I get 12 minus 5 minus 4 is equal to V2. And that gives me V2 is equal to, what is this, 9, 3. So I have 3 volts. Now again, I could use Ohm's law to figure out this and this. So V is equal to IR. You can do this calculation yourself. V is equal to IR. And we can always check, right? Here, 5, this is a series circuit. So I know the series circuit, the resistance is add normally. 5 plus 3 is 8. 8 plus 4 is 12. Good. I have the same resistance. My current is the same in all of them. And my voltages add to 12. So for all these problems, in your next lesson, you're going to be learning about parallel circuits, and then after that, combined circuits. But for all of these problems, if you can simply just apply Ohm's law and your 2 voltage laws, you'll be fine.